So yesterday we were talking about what are called sex-linked traits. These are traits that are specifically carried typically on the X chromosome. And we had left off with this fruit fly example. So fruit fly, the color of their eyes, red or white, is on the X chromosome. So females have two X's. So a female, if she was X big R, or X big R, X little r, she would have red eyes. A male, on the other hand, to have red eyes would have to be X big R, Y. So this would be a male with red eyes. A female with white eyes would be X little r, and a male with white eyes would be X little r, Y. Now I point this out because this is what makes sex-linked traits very unique, the fact that females have two copies of the X, but males only have one. Notice we do not write a letter on the Y. The Y chromosome, remember, is a completely different chromosome. It does not have the same genes as the X. So a male is either going to have red eyes or white eyes dependent upon his X, whereas a female is going to have red or white eyes, and she can actually be a carrier like this, X big R, X little r, where she is got red eyes, but she's heterozygous and carries the gene for white eyes. A male cannot be heterozygous for a sex-linked trait. He either has it or he doesn't. And so here were some specific crosses. So here's a red-eyed female and a white-eyed male. This is a purebred red-eyed female that they're crossing here. See how you do the Punnett square. So they only did 2 boxes here, and I've shown you how to do that, but some of you still prefer to do 4 boxes. So just to show you with 4 boxes, you would do, they're using, so the X little ry, so this is our male. He gives either the X or the Y. Remember, we're representing the possibilities. The female with red eyes, she's homozygous in this scenario. So she's X big R. So this is what it would look like with 4 boxes. You're going to get the same answer. So in this case, if you look at our results, notice how they colored everybody in. Everybody has red eyes. It doesn't matter if you're a boy or a girl, you are going to have red eyes, because everybody has a copy of big R. Now, it turns out that these females are carriers. That's what you call them, remember, that they carry the gene for white eyes, but they don't actually have white eyes, but they could pass it on to their offspring. The male offspring here are red-eyed, and they do not even carry the gene for white eyes. Here's the scenario now with technically one of the offspring, the F1, from that original cross, we have big R, little r. So now we have one of those females that was a carrier. And look what happens. When we cross her with a normal male, notice that we get all red-eyed females. So all of our females, all would have red eyes. But in our males, we get half with white eyes. Half our males red, half white. And this is actually how sex-linked crosses were discovered. Thomas Hunt Morgan, studying the fruit flies, he noticed that there was, when these traits came about, it was different in males versus females. That in fact, in these cases, a lot more males show up with these traits than females because they only have one X. Here's another example. In this case, we're crossing a heterozygous female with a homozygous, with a recessive male, a white-eyed male. He's not homozygous. He's only got one X. Sorry. And again, notice our female, she can give big R or little r, and the male gives little r and y. And in this case, what we end up with, interestingly, is we do end up with half of our females and half of our males both with red eyes, and then the other half of our females and half of our males with white eyes. So in this case, we do actually end up with the same proportion of red versus white. You could just say half of all the offspring would be red-eyed and half would be white-eyed in this particular cross. But in a lot of cases, you're going to see these traits more common in males, like here, where only males end up with white eyes. So here's a practice problem. Cross a white-eyed female with a red-eyed male. So let's see what happens here. So we have a red-eyed female, and we're going to assume white-eyed female. Oh, so white eyes is recessive. So our female has to be X little r, X little r. That's the only way that she could have white eyes. Our male only has one X. and it says he has red eyes, so his X must have the big R. Now this is actually a really interesting one. Look what's going to happen here. So now we do our cross, we put our X's together, we get X big R, X little r, X big R, X little r. So our females all have red eyes. And now our males, X little ry, X little ry. Wow. So like this, our males all have white eyes. So in this case, our males and our females, their eye color will be completely different. You would actually be able to identify which flies were male or female by their eye color in this cross. You would know, because all the males are going to have white eyes and all the females are going to have red eyes. So this is an interesting cross. Now, there are some human sex-linked disorders we mentioned earlier. Most of them are recessive, not all of them. Here's the thing. Males will only get these traits from their mom. Only from their mom. So if you are a male and you are colorblind, you would never, ever have to worry about passing that trait to your son. Ever. Because in order to have a son, so let's say I'm little r, X little ry, right? And let's say this is for being colorblind. Well, if I have a son, what am I gonna give him? I'm gonna give him the Y. But if I have a daughter, I am gonna give her my X. So if a male has a daughter, he would give this X carrying the trait to her. But here's the thing. The only way a girl can show the trait is she's got to get a copy from both her parents, right? Most of these traits are pretty recessive. And this is why we almost never see colorblind females. We almost never see hemophiliac females with the bleeding disorder. Because in order for a female to get this disorder, she'd have to have a dad that has it, because he only has one X. So he would have to actually physically have the trait. And then her mom would also have to at least be a carrier of the trait, right? And these are not that common of traits. So the chance of this happening is pretty low. But there are females who are colorblind. There are females with hemophilia. But it's definitely much less common than males. So males, when they get these traits, they always get them from their mom. And a lot of times, the mom doesn't actually show the trait. It just appears in the son, and it's like, hey, where did this come from? Oh, well, the mom was heterozygous. And she didn't actually have the trait, but she ended up passing it on because she was a carrier of the trait, so it's sort of hidden. Let me get rid of my work here. So, hemophilia and blood clotting, is a blood clotting disorder. This is an example of an X-linked trait. So Tom and Sue do not have hemophilia, but their first son does have hemophilia. So they want you to do sort of a logic problem here and figure it out. So Tom does not have hemophilia. Well, since hemophilia is recessive, Tom must be big RY. Not really sure why I picked R for that. Just use R. Now, Sue does not have hemophilia either, but if they had a son with hemophilia, so their son is this. Well, we know that the son got the Y from dad, which means he had to get his X with the hemophilia from mom. So she does not have hemophilia, but she must be a carrier of hemophilia. And so now we know what the parents are. So this is Tom, this is Sue, and then you could figure out the probability of having more children with hemophilia. You could do this cross. So X big RY, X big R, X little r. And what we would see is the chance of them having another child with hemophilia. Technically, we should separate this out by sex. So the chance of a daughter with hemophilia is actually a 0% chance. They cannot have a daughter with hemophilia because as long as the dad doesn't have it, she's going to get a good copy from him. Chance of a son with hemophilia, a little bit different. Chance of a son with hemophilia, 1 out of 2. 1 out of the sons would be likely to have hemophilia. The hemophilia was actually considered a royal disease. It was very common in the royal family. And in this pedigree, we've talked about pedigrees, they're actually showing the recessives, the carriers as half-colored in, which I haven't shown you before. But half-colored in means that they're heterozygous. This is a sex-linked trait, so she would have been like X big B, X little b. Albert does not have it, so he'd be X big B, Y. Alice got the bad gene from her mom, but the good gene from her dad. So she also is a carrier, but doesn't actually have hemophilia. Lewis does not have hemophilia. Alexandra also got the gene from her mom, but again, she's just a carrier. Nicholas did not have hemophilia. The son Alexis now gets the bad gene from mom, gets the Y from dad, and there you go. We have hemophilia in the son. So notice how in a sex-linked trait, what we usually see is sons end up with it. Females are typically just carriers. We almost never see a female that actually has it. And if you see a pedigree where you see carriers colored in, half colored in, and the carriers are only females and males either have it or they don't, that's usually a sign that it's a sex-linked trait. Because if it was a regular dominant recessive trait, you could have males that were carriers too. But you can't have a male carrier if it's a sex-linked trait. A male's either, because he only has one X, so he's either going to be X big BY and not be colored in, or X little by and be colored in. But the females could be carriers and be half colored in. So that's actually a clue that something is a sex-linked trait in a pedigree. All right, and that's actually it. That's the end of our chapter. So we'll be reviewing in class, and we're going to do a lab activity on this as well, and then our test will be next week.